Hello, it's Z here, and welcome to the fifth video in a series of videos that I've been creating related to using the tools of linear programming to help optimize capital budgeting. So if you've just joined us for this video, you may want to try and go back and watch the previous few videos so you can catch up with what we've done so far. As a quick recap, we've looked at a number of different scenarios of varying complexities, and where we last left off, we were at quite a challenging problem where we use a whole bunch of different tools that wasn't just Excel, but also extended into using code in Python to try and solve the problem, and also making use of additional add-ins. And you can see that we've had a bunch of different results. And this is also a tricky problem because it's not a straightforward convex problem, because what you can see is you have multiple solutions that are different, that have the same NPV but have a different configuration. So you can see this one was 54.6, but it was like this. But if you solve it using a different solver engine, you get 54.6 as well. But you can see these two end up being different, and but they end up producing the same NPV. So it's a tough one. But I guess that's part of the whole process. Now we're gonna try and make this even more complicated, because I've got a new scenario here, which is basically the same scenario as before, but now we've got an added complication where we're going to be using variability in the capex and also the benefit per year. And the way that the uncertainty is reflected is using a risk distribution that I've mapped over onto the capex figures and the benefit figures that changes every single time. So if I click any empty cell, and let me just do that, you can see the numbers dance around. And we're going to try and make the solver solve for different permutations of numbers. Now, the risk distribution itself is called I'm using something called a beta-PERT distribution. And beta-PERT distribution is quite often used in these sort of Monte Carlo risk simulations, because it's very easy to set up in terms of getting the inputs, because it uses a minimum, a maximum, and a most likely figure that you normally get from existing domain experts, and you convert it into some indicators that you can stick back into a beta distribution. And the end result of all this is that you get a number that falls between the range that you've set, where it tries to follow the most likely number. And the shape should be illustrative as per below. So if you do it perfectly symmetrical, you get a normal distribution, but you can also have distributions with a long tail, depending on how you set it up. So we are going to be doing that. And for simplicity's sake, I've made each of the distributions independent, meaning that they're not correlated with each other. If you are familiar with Monte Carlo simulations, you probably know that you can also simulate relationships or correlations between risk distributions, so that if one is high, the other one also falls into a high end. I haven't done that here, but because it's not simple to do it in plain vanilla Excel, but there are tools that you can use to do that. So here I've got an add-in that I just wanted to show. It's called Excel Risk, and those of you who've used things like Oracle's Crystal Ball or Palisades at risk will find this very familiar, because it's a free open source tool that allows you to do many of those things. So you can write a distribution using the Excel risk, and there's also an advantage that it's more random, because the basic algorithm that Excel uses to generate a random variable isn't really random, but Excel RIS uses a different sampling technique and gives it a bit more of a randomness. Now, I'm not going to do that here, just in case you don't want to use more add-ins. So we'll just stick with Excel for now, so the variables are not correlated. Now, the solver model itself has been set up in the same way, where we are trying to maximize the the NPV over a 3-year window, except now the benefit per year is variable, and you're trying to stay within a constraint of a certain threshold, sorry, a certain ceiling per year. But the numbers themselves are also variable, so the capex numbers also change every single time. Now, if you were to naively try and solve it like this, you'll get an error message because the solver cannot handle the fact that you've got random variables in the model. So it's going to spit up an error in a moment, like so. And you could try and run it using the GRG nonlinear, but you don't really get much better results. Now, I took a different approach where I have instead created a bit of a background script where what it does is it cuts and pastes the risk capex and the risk benefit into a different table. And by doing that, the numbers become static, and solver can in fact handle it now because you're solving per realization rather than trying to solve on the fly. And I'm using some VBA code in the background to do this. So let me just try and show you what it looks like. So I reset the solver model, where the solver model has gone from this setup to this particular setup, where it's the same thing, except now I'm referencing the table on a per iteration basis. So rows 20 to 29. And just to demonstrate what that looks like. So here it's the numbers don't keep changing, so it's a single number, but it was one of the permutations. And if I hit solve, it takes about maybe 5 to 10 seconds, but the Excel solver will do its magic and it will solve for the problem. And it's found a solution. May not be the most optimum, but it's found a solution for this particular problem. And let me just click, okay, yeah, that's fine. We're going to overwrite it anyway. So what I've done is I've made use of some VBA code where is that? It's over here. Yes, where what it does is just walking through it on a very high level. You specify the number of iterations. I'm just going to put 30. What it's doing here is it's cutting and pasting the cells from the top that are random and pasting it to the table below so that it becomes static. And it's running the solver. And every time a solution is generated, it is storing the NPV and also this configuration of which projects happen in which year in an array, and storing it over the number, how many number of iterations that we've chosen to do. So you can think of it in the sense that every time you shake the dice, you get a different number. It's cutting and pasting this and then solving it and copying this and putting it somewhere in the background. Now I'm going to run this macro just to sort of give you a demo of what it looks like. Okay, let's go. Run. It's going to take a bit of time because you saw a moment ago that I switched it up to 30 iterations just to get a bit of a feel of what sort of results you could see. So I'm going to hit pause. And we're back. and you can see it took about 8 minutes or so. Not so bad, I guess. I'm going to click OK. And what it did is it generated an array that's now spat out into another sheet where basically there are 30 iterations, and for every single iteration, it is storing a value for the various projects for the various years and the net benefit. So I'm just gonna give you an example. Each one of the iterations produce a certain solved solution with this total NPV sum at, say, for example, project one for project, you can see in iteration number, say number 3, it took project 1 took the value of year 1. So basically this is just a table that collects all the information and dumps it into a this form, which is not very useful for what we need, and transforming it into something a bit more readable. This is the same thing but represented per iteration. So you can example click 2, and you can see that in iteration number 2, these were the permutations that the various years took, and this was the benefit that was generated from that particular permutation. And you can do the same where you can look at a different iteration. Now, how does this help us? Because we're trying to find the best set of which year to put each project in for all different outcomes. And it's one thing to look at the what you would call the variability in the benefit, but what you really want is you want the variability in the entire solution. If that seems cryptic, let me explain it this way. So if I were to select all 30 iterations and I were to show the average rather than the absolute value, you see that for project 1, 50% of the time, the optimum solution is in year 2, and for project 5, 80% it's in year 2, but there's sometimes it's in year 3 or year 1. Now, the problem is you can't just pick the highest score for each one and plop it in, because it's the co-occurrence of different years for the different projects that matter. So the way I've worked around that problem is I've created a table where if you sort this, let's see, refresh, and we're going to try and sort highest, largest to smallest. You can see that the this particular configuration seems to have occurred most frequently. Well, not that frequent, but I mean, it's 3 times more than most of the others out of the 30, so we haven't run this enough. But the principle is if you run this, say, 100 times, you probably get a better picture of which one is the most optimal solution. So example for this one, if we were to try and take that here and translate it, copy this, and we paste it back into this bit here. So this is the, with the limited number of iterations, this is the best decision variable set that satisfies the conditions, that gives you the highest probabilistic benefit. So in that way, we've managed to also incorporate uncertainty into the model. Now, this is a bit slow, so I'm going to see if we can scale it up and speed it up. Now, rather than try and do everything in Excel, I'm going to use Python instead. So the last video you saw that I used Pyomo, but I've gone back to PulP because PulP is a bit of an easier library to sort of write syntax-wise, and I've used a few additional libraries for the random number generation. So SciPy has a stats module that can give you a beta distribution, so that was really useful. And let me just run this for you. So if you're wondering what's going on, the first step is I'm loading in the model. So this is just the same information as before. This is just a check to make sure stuff came across properly. And this bit here is using the minimum mode and maximum values to generate a random variable. Sorry, to generate the alpha and beta parameters that you need for the random distribution. So you'll see now that it's got max min mode translated into alpha and beta, which is what you need for the distribution. I'm creating some blank arrays to store the values for each iteration. And this is the table with the this is the cell where I am running multiple iterations where in each loop I am generating a fresh set of random variables for the solver engine in PulP to work on. And the rest of the code is actually similar to what you saw in the third video where I showcased an example problem in PulP. So it's the same thing. And at the bottom here, I've got some code that collects the results from each iteration and puts it in a way that the arrays that I set up earlier, well, it's a list in this case with Python, the list starts to collect all the different results from the NPV and also the configuration that led to that NPV for that particular iteration. So that's a lot of words. Maybe it's best just to see it in action. And I've done this earlier, so I know that it can do it faster than Excel, so I'm just going to run it for 100 iterations. And we've got a timer here to check how long it takes. So I'm going to run it, and it's thinking. And I'm going to pause this video and come back when it's done. And we're back. And the total time it took to run 100 iterations was only 30 seconds. So remember when we did it in Excel, it was almost 8+ minutes. So this is a big improvement. Maybe it's also the way that I've been using the arrays in Excel, but somehow it seems that running it in Python using PulP is a lot quicker. Now, this actually isn't very useful because it doesn't tell you the results. So instead, I'm going to show you this. So this is a list of all the different optimal configurations where just like in Excel, this is project 1, project 2, project 3. So basically, project 1 is in year 2, project 2 is in year 4, project 3 is in year 2. So basically, it's a sequence of which year for which particular project, and there are 100 of these. And this is all the different optimal NPVs given the risk values per individual project. Now, if I were to try and plot it and say, let's put 20 bins, maybe, you get a distribution where you can see it's a bit of a shape here and you can find what the P50 is, but that's not so useful what you want is you want to find out what is the optimal configuration that given all the different permutations. And we can do that here, where you can see this is a nice feature in Python that allows you to iterate over a list and pick out frequency of occurrences. And you can see this particular configuration has occurred 18 different times. Given all the different range of capex values and benefit values, this configuration of which project to select for which year has cropped up a lot more. And you want to see that visually, it looks a bit like this, where that high bar here, 18, is this. So we have found a way to pick the optimal decision variable set given a certain range of uncertainties for the model that we set up. And we've done it in a reasonable amount of time. So that sort of brings me to the end of this scenario number 5. Now, the next video will be the same thing, but instead of using a DIY solution, we're going to be using a commercial tool called Analytic Solver. So check back in for the next video if you want to see how that goes.